Now let us consider an example. We can show the image. This image consists of two graphs. Let us see the first image, where the first image consists of four spicy candies and four sweet candies. Okay, so let us consider the red color as the spicy candy and the blue color as the sweet candy. Now it has to be formed as a cluster. So when you visualize this, it is easy. Red candies from one cluster, blue candies from another one. So the model can easily learn if the color is red, then it is spicy, and if the color is blue, then it is predicted to be the sweetest one. With just one feature and two categories, the algorithm performs beautifully. This is what we call low dimensional well structured data. So it is easy to learn, visualize and interpret. Now increasing the complexity. Now imagine the factory expands its product line. Instead of two colors, you now have 8: red, maroon, pink, flamingo, blue, turquoise, seaweed and ocean. So these are all the 8 colors. Let us consider these 8 colors, and we have to segregate it based on the two data sets. One is reddish and the second one is bluish. So now for a human eyes, it is easy to recognize either it comes under the red candy or it comes under the blue candy. But we intuitively know that pink is a lighter shade of a red and turquoise is a bluish green. But to a computer algorithm, each color is a completely independent variable, so an entirely separate dimension. So the algorithm now sees the data like this. Each candy color is a new axis in an 8-dimensional color space. No relationship exists between pink and red unless explicitly defined. Now the model's world becomes overwhelming complex, and the simple spicy or sweet distinction gets lost in a sea of meaningless features. So as dimensions multiply, strange things happen. So the algorithm concludes that each candy is unique, forming its own separate cluster. It has no longer tell that pink and red are similar. All colors appear equally distinct from each other. So the model incorrectly assumes there are 8 clusters, each color equally distinct, and each cluster is equally related to spicy or sweet. It is like teaching a robot about colors but never explaining the red and maroon or close relatives. The robot will treat them as completely unrelated. So it will be like this. So the for a machine, it is difficult to understand whether this belongs to red or maroon or pink or orange, whatever it is. So as dimensions multiply, strange things happen. The algorithm concludes each candy is unique, forming its own separate cluster. It can no longer tell that pink and red are similar. All colors appear equally distant from each other. So the model incorrectly assumes there are 8 clusters, each color equally distinct, and each cluster is equally related to spicy or sweet. It is like teaching a robot about colors but never explaining that red is a close relative to maroon. The robot will treat them as completely unrelated. So this is how exactly what happens when the model loses feature correlation in high dimensional data. So this misinterpretation leads to many serious problems like loss of grouping ability, inability to generalize, and wrong predictions might happen. So the model cannot form meaningful clusters because all features seem equally distinct. Inability to generalize a new candy of an unseen color will confuse the model. It won't know where to place it. Wrong predictions. Since all clusters are equally similar, the algorithm might randomly assign spicy or sweet labels. Thus, even though we added more data, our model's performance deceased the exact opposite of what we expected. This is a perfect example of how the curse of dimensionality manifests in real world problems. Let us see. Now, instead of two categories of colors, we have 8. Now, let us see how it works.